Hello and welcome to this lesson brought to you by Bitmerge. This lesson is about solving the problems of negative numbers, addition, and subtraction using bits. We'll look at a few approaches and discuss the issues as we go. If you aren't familiar with bits, you might want to check out our video on bits and bytes, linked in the description. Let's talk about signed magnitude first. This approach, just like the other two approaches we'll see, tries to solve the problem of representing negative numbers on bit patterns. It does this by taking a bit pattern, like this 4-bit figure, and reserving the most significant bit, the leftmost bit. This becomes the signed bit, and a 0 indicates that the remaining bit should be treated as positive, while a 1 indicates the remaining bit should be treated as negative. For example, these 4 bits hold the value 3. Changing the signed bit from 0 to 1 would indicate that the following 3 digits are negative, giving us the value -3. This is the essence of signed magnitude. While this seems like it should solve the problem of negative numbers, it actually does not. If we wanted to subtract two numbers, we can do so by addition. 3 minus 3, for example, is the same as 3 plus -3. In this example, 1 plus 1 is 2, or 1, 0, so we write the 0 and carry the 1. 1 plus 1 plus 1 is 3, or 1, 1, so we write the 1 and carry the 1. 0 plus 0 is 0, plus the carried 1 is 1, so we write the 1. Finally, 0 plus 1 is 1, so we write 1. This gives us the curious result of a -5 for 3 minus 3. We need a better approach. 1's complement takes a different approach to negative numbers. It also uses a sign bit at the beginning of a number, but does something else as well. To represent -3 in 1's complement, we flip the signed bit, then flip all bits following the signed bit. -3 in 1's complement looks like -4 in signed magnitude, but we're using 1's complement, so it is -3. Now, subtraction is a whole lot easier. Adding -3 to 3, we get 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 1 is 1. The answer we're looking for is 0. We can tell immediately that our result is negative by the sign bit at the beginning. Following 1's complement rules, we can tell what negative number this is by flipping all of the bits following the signed bit. The result, 1000, tells us that 1111 represents -0. While this is certainly a much better result than signed magnitude gave us, we still have a problem. -0 doesn't make a whole lot of logical sense. Finally, here's where 2's complement comes in. If you understood 1's complement, you'll have no problem understanding 2's complement. 2's complement says that to get a negative number, we take 1's complement and add 1. That is, we flip the first bit, then flip all remaining bits and add 1 to the result. To the number 3, we flip the sign bit, then flip all subsequent bits and add 1 to our result. 1101 now represents -3. Interesting. Let's do the subtraction. 3 minus 3 is the same as 3 plus -3, so from right to left, 1 plus 1 is 2, which is 1, 0, so we write the 0 and carry the 1. 1 plus 1 plus 0 is 1, 0, carry the 1. 1 plus 0 plus 1 is 1, 0, carry the 1, and finally, 1 plus 0 plus 1 is 1, 0, so we write the 0, and, since there are no bits left to store the carried 1, 2's complement says that we simply discard it. This result gives us what we're looking for. 3 minus 3 is 0. 2's complement successfully solves the problems of storing and manipulating negative numbers, but recognize that by sacrificing the first bit for flagging the sign, we're changing the range of numbers we can represent. 4 bits can represent the numbers 0 through 15 without a signed bit, and -8 through +7 with a signed bit. A byte can represent 0 through 255 without a signed bit, and -128 through +127 with a signed bit.